examples for differentiation and integration of transforms. So we apply those two formulas to do some calculation. Yeah. Before we do that, those examples, I like to start with proof of the convolution theorem. Yeah. So there is a place I need to explain a little bit. Yeah. Because first, not very hard, but second, we are curious. So why there is such a nice property? Yeah. All right. First, the definition of convolution. Yeah. Little h equals little f convolute little g. Yeah. So the definition is given in this integral. Yeah. So our goal, we want to prove the Laplace transform capital H. Yeah. Laplace transform of little h. So capital H equals the product of capital F and capital G. So we need to calculate the integral. Carefully. So here there are several places we need to be very careful. All right. First, when we start from the definition of Laplace transform. Yeah. Capital F of S. Yeah. Just write the definition directly. Yeah. This integral. Yeah. Then capital G, we also write it in the definition, but because we need to mix. When we do the multiplication, we need to mix these two integrals. So we intentionally use a different integral variable, dummy variable p. Yeah. Yeah. Try to make it different from the one in the first integral. Yeah. Tau in the first one, p in the second one. Yeah. Otherwise, very easy to get confused. Yeah. All right. Then, so we need to do the product. But when we do the product, we try to target the structure of the convolution structure. Here, the convolution structure, the product of little f function, you compare with the functions we have here. Okay, all right. F of tau corresponds to f of tau here. Yeah, so that's perfect. So nothing to change. But the g of t minus tau and g of p here, slightly different. So we want to make them match. Yeah. So then we do a variable substitution. P equals t minus tau. Yeah. Or, because here in these two integrals there is no t, right? So we write t equals p plus tau. So we introduce a t variable. T, new variable, t. T is defined as p plus tau. Then we can replace p by t minus tau. Yeah. Variable substitution. So in the second integral, we do variable substitution. Yeah. So let's write it carefully. Yeah. All right. But when we do variable substitution, we need to change the integral limits. So the p equals 0, from the first g integral form. When p equal to 0, t equals tau. So then we need to change. Here, the dummy variable becomes t. But the t starts with tau. So that's why we need to be. Justin?
I was my page 7 doesn't match that page.
Yeah. I add a new page.
Oh, okay.
Yeah, I add a new page. Yeah.
All right.
Yeah. So yeah. So I will upload this newer version. Yeah.
Okay.
After class. Yeah.
Okay.
Yeah. The old one I do not have time to replace it. Yeah. So here I insert a new page. Yeah. All right. Yeah. So now we need to do the variable substitution. Straightforward variable substitution. Yeah. So this step, yeah, you need to be careful on this lower integral limit. Yeah. Yeah. All right. Then after that, yeah, we simplify it. We simplify this integral, but you need to treat t as the variable, dummy variable, tau as constant. Yeah. So here tau is constant. Yeah. Tau is constant. That means this e to the negative s times, multiply through, e to the s tau, nothing to do with t. You can factor it out. Yeah. So you factor this e to the s tau. No variable, right? So constant, s and tau, both constants. So you factor this e function out. That inside, so you have that current form. All right. Now, we are ready to calculate a product of f and g. What is f and g? The product of capital F function and a g function, yeah, we multiply these two integrals. Yeah. Okay. Yeah. So when we do integral multiplication, yeah, we can multiply inside. Yeah. So here we multiply inside. All right. So this whole function, yeah. So here, yeah. Multiply, yeah. So here you can see we use the double integral. Double integral, the inner one, t, yeah. dt in the inner integral, yeah. Outer d tau. Okay, yeah. All right. So this function, yeah. So multiply, yeah. Right. Yeah, because here you can see why we can multiply inside. So here, so we multiply together, yeah. Multiply these two integrals together, all right. All right. Right. Yeah. So here, yeah, because we treat the tau as constant, right? Yeah. But when we do multiplication, yeah. So here you can see, in this integral, s is constant, right? Yeah. Yeah. So s is constant. So think in this way: s is constant. Yeah. So this is g. Can we, when we do multiplication, g of s here, can we put the g of s inside? Yeah, because g of s inside the integral. Yeah. Yeah. Multiply inside the integral. All right. So now inside the integral, then we copy it here, okay? But the way we do it, the inner one should be dt, because the inner one contains tau. This tau is used in the outer integral. Yeah, so that's why this order is important. Inner one used dummy variable t, and the outer one used dummy variable tau. Yeah, all right. So this place a little complicated. All right. Then next step. Yeah. Next step is a critical step. Yeah. The critical step, we did this kind of thing last time. Yeah. So here we need to do it again. That's the interchange of two integrals. Yeah. Interchange these two integrals. Interchange. Okay? Make the inner integral outside and make outer integral inside. Change the order of two integrals. Yeah. For double integral, we can do that. So interchange. But when we do the interchange operation, we need to check the condition. So there must be some condition. Yeah. Yeah. So, yeah. But there is a theorem I mentioned last time. Fubini theorem, if the integral function, yeah, the integral function, so here, the product, this one, you know, for the double integral, if it is absolute integrable. Yeah. So the condition is if it is absolute integrable. If you take absolute value, it's still integrable. Yeah. Yeah. So here we use the, Laplace transform exists, so there is a inequality. So we use that. It's absolute value. So the absolute value, product of all these functions, integrable for this double integral, then we can exchange the order of the integrals. Here we can do it. Yeah. All right. Next step, we need to do the interchange of two integrals. But when we do it, we should be very careful. Yeah? Because the integral limits, we need to change the integral limits when we do that. All right. Yeah. So we need to make d tau, yeah? So in the inner integral and the dt in the outer integral. Yeah. So these two also change. Yeah. d tau inside, dt outside. Yeah. But when we do that change, we need to calculate the integral limits carefully. Yeah. So here I need to draw a diagram. Yeah. Here, first let me write it. After interchange, we get this. After interchange. Okay. Inner integral, the integral limit. Oh yeah. This is before change. Okay. Yeah. So here I write another formula. Clean up. Yeah. So here, because we can simplify a little bit, right? Yeah. Because this e term, this e can be canceled out. Yeah. So after cancellation, we have a clean version. Clean version here. Right. We do the interchange. Yeah. For this clean version, we do the interchange. Right. After interchange, we get this one, but here you can see there is an important change I need to explain. Yeah. Look at the inner integral. The integral limit from 0 to t, right? So here, the biggest change is the integral limits. Yeah, some change. Let me explain. How do we get the inner integral limits change in this way? Yeah. So other things looks fine, other parts, but the main change is in this inner integral limits, this part. Yeah. All right, let me draw a diagram to explain. Let's look at the area that we do the integral. double integral. Yeah, double integral, the domain, the function, yeah. So the area, so we need to work on. So there's two variable, dt variable, d tau variable. Yeah. We want to see. So let's say this is tau axis, this is t axis. All right. dt from tau to infinity. Yeah. So let's draw straight line. So this straight line has the equation t equals tau. Yeah. All right. T from tau to infinity. Is it this part tau to infinity? Yeah. So you start from this line. Okay. Yeah. Yeah. Because this line t equals tau. Okay. You start from tau, then you go to infinity for t. T. Yeah. So. Sorry. Start from tau to infinity. Yeah, because t, right? Here we look at t. Yeah. So you start from tau, then your t grow to infinity. Okay. So that's this part. You start from tau, then you go to infinity. Yeah. So So the area you work on is this, triangle area. Yeah. All right. Now, after you switch the integral order, this area cannot change. We still use the same integral area. Yeah. But we do inner integral using the tau variable first. Yeah. So we look at the tau variable. Tau start from, yeah, so the same triangle, but we look at the tau value change from 0 to t, right? Yeah, because we always start from 0, then we end at t. Yeah, this line is t, okay? Yeah, so that's why for this inner integral, the d tau, the lower limit is 0, the upper limit is t. Yeah, same area. We cannot change the area. Yeah. So then outer part tau from 0 to infinity. Yeah. So that is so when we do the interchange, we need to, get so using the integration, this area, to help us figure out the integral limits. Yeah. All right. Now we can get to our destination. Yeah, because this inner integral corresponds to the definition of convolution, right? Yeah. So it corresponds to the definition of convolution. So it is the little h function. Little h function, okay? Yeah. So the whole inner integral equals little h based on the definition. So then outer integral, just the definition of Laplace transform. So we can see it equals the capital H of S. Yeah. So we prove the convolution theorem. Yeah. Yeah. So here, yeah, because several places a little hard to understand. Yeah. So I explain here. Yeah. Otherwise, yes. Otherwise, if you read the textbook directly, probably many students may not be able to understand. Yeah. Especially the interchange part. Yeah. The interchange part. Why we need to change integral limits in this way. So draw this diagram. Yeah. Yeah. All right. Yeah. All right. So next, yeah. So let's work on some examples. Yeah. Example for integration of transform. Here, yeah. So I copy the formulas below, yeah, so we can, apply it, yeah. Calculate the inverse Laplace transform of this log function, yeah. So here you can see, yeah, log function, yeah. Yeah. Here, think about if you apply the definition, well, it's a log function. Yeah? So in our basic formula, we do not have that part, right? The basic formula, yeah. All right, yeah. So here, there is an important step, yeah. Because we want to represent the log function as integral of some function. Yeah. Yeah. So here, this step. Yeah. So let me explain this step slowly. Yeah. All right. So here, this is an important step. Yeah. All right. We want to find a capital G function such that our natural log function equals the integral of this G function. Yeah. So if we know we want to do this, then it's very easy to find the G function, right? Yeah. Because we just take a derivative, both sides. Yeah. Right hand side, yeah, by the fundamental theorem of calculus, fundamental theorem, but this variable is at the lower limit, not the upper limit. So when you take the derivative, the derivative of this integral should be negative G, capital G. Upper limit, positive. Yeah. Lower limit, yeah, negative. Yeah. So then, the derivative of the log function, yeah, so you know how to find it. Yeah. So let's calculate. Yeah, so that's the, yeah. So here you can get a capital G function as a, simpler function because no natural log anymore. Okay. No natural log, so you know how to calculate the inverse Laplace transform, right? Yeah. All right. Then, yeah. So after simplification, this is a G function. Yeah. All right. Then we can calculate inverse Laplace transform of G function easily. Yeah. Okay. All right. Basic formula. The first basic formula, we can calculate inverse Laplace transform of the first term. Then another basic formula, cosine. Yeah, we can calculate Laplace transform of the second term. Yeah, so now, little g function can be found as 2 minus 2 cosine omega t. So now we can apply the integration of transform formula. All right, yeah, so here, see? Here you can see. Yeah, so this is what we want to do. Capital G here, little g here, right? Yeah. So we apply the second Laplace inverse formula. Yeah. So then we can write the final result. Yeah. Equals this integral. Yeah. Then by that formula, little g of t over t. Little g, we have it. Over t, yeah, so we can write. Yeah. here you can see, yeah, when we have this integration of Laplace transform formula, yeah, we have more tools, right? So this is another tool we can use to find Laplace transform, inverse Laplace transform. Yeah? Yeah. Yeah. All right, so this example. Yeah. But the first step is important. Yeah, first step. So you need to have some experience. Yeah. How do you know? Right? Yeah. Yeah. But one thing you know, the derivative of this function, after you take derivative of this natural log function, the natural log is gone. Yeah? So this property, you know it. Yeah. So you know, yeah, if we want to remove the natural log, we should take derivative of this function. Yeah. But the way you take derivative, yeah, so you have to have some function, yeah, because you cannot just take derivative directly, so you need to find appropriate function. Yeah. So when you take the derivative, yeah, so there is a specific function corresponds to that derivative. Yeah. All right. Yeah. So this example. Yeah. Then a second example. Yeah. So we solve ODE, special ODE, Laguerre's equation. Yeah. So this ODE has this special property. Yeah. T y double prime plus parenthesis 1 minus t y prime plus ny. Yeah. Yeah. So there is some background for this ODE. Yeah. So here we do not look at the background. We just solve it. Yeah. Here you can see, yeah, if we use our, think about, if we do not use Laplace transform, yeah, you can see it could be very hard to solve. Yeah. Yeah. Although the ODE is not complicated, yeah, but it's not that easy to solve. Yeah. All right. So here, let's use the Laplace transform to solve it. Yeah. Yeah. These two formulas, derivative, second derivative. Yeah. All right. And yeah, another formula we want to use. T, yeah, this formula. Yeah. This is the differentiation of Laplace transform formula. Yeah. So yeah, we just learned differentiation of Laplace formula. Yeah. Yeah. All right. So let's take Laplace transform both sides. Yeah. All right. T, yeah. So the structure, look at the structure, right? Yeah. Yeah. Easy, but you have T. When you have T, right? When you have T, you can use this formula. Yeah. All right. Yeah. So Laplace transform of y prime. Yeah, that's easy. Yeah. So the second term, easy. Yeah. All right. Then this term. Yeah. Yeah. All right. Take a negative derivative with respect to s inside, yeah, because this is, so here, inside y prime. So inside is the Laplace transform of y prime. Yeah. So that's why. So we have this. Yeah. Yeah. Right? Yeah. Because inside, capital F on little f, Laplace transform on little f is y prime. So Laplace transform on y prime. So that's this function inside. Yeah. All right. So then, yeah. All right. Yeah, constant, right? Yeah, constant, then product rule, right? Yeah, product rule, so we have this. Yeah. All right, that's this term, this term, this term, the last one, we need to do this one. Yeah. All right. L of double prime, yeah, so we apply that formula, so we have that. Right. Then T, yeah, so that T formula, T, d negative d over ds on that Laplace transform of y double prime. Yeah. Yeah. So constant term gone, yeah. So product rule, right? Yeah. Product rule. Yeah. All right. So after simplification, we have this one. Yeah. Then we add them up. Yeah. Yeah. All right. So here, let's add them up. Yeah. So we copy this part here. Yeah. Then the second term Laplace transform, copy here. The third term Laplace transform. Yeah, minus, right? Yeah, minus. So we change the sign, minus plus sign. Then the last one, yeah, n times y, yeah, adding together. All right. Cancellation, yeah, yeah. All right. So then we write this ODE, yeah, capital Y. So still there is a y prime. Yeah, yeah, because by the chain rule, right? Also, not chain rule, product rule. Product rule. So we have a capital Y prime. Yeah. So here you can see, yeah, this case slightly different from our previous examples. Our previous examples, after we apply Laplace transform, we have an algebraic equation, right? Yeah. But this one, after we apply Laplace transform, we still have an ODE. Okay? Yeah. But it's a simpler ODE. The order is reduced. The original equation is second order. But now after we apply Laplace transform, it becomes a first order ODE. Yeah. So that's the, yeah, something different from our, all those previous examples. The special property of this example. Yeah. So we need to solve this first order ODE. Yeah. So separable, right? Yeah. So we use the separable technique, yeah, to solve it. Yeah. S part, Y part, yeah, can be separated easily. Yeah. So then we take yeah, so integration, we can find y equals this one. But the y, capital Y, we need to take inverse Laplace transform. So this function, we need to take inverse Laplace transform. Yeah. So the last step, yeah, but it's inverse Laplace transform, yeah, because here, yeah, when we look at inverse Laplace transform, the numerator, we can apply binary expansion, right? Binomial formula. Binomial formula, we can expand the numerator functions, many terms. Then, each term, we can do division. So, denominator division. So, term by term. So, when we calculate inverse Laplace transform, we can calculate inverse term by term Laplace transform. Then we can apply our basic formula. Yeah. But that's a long polynomial, right? Yeah. So term by term is a, yeah. Although we can calculate each term, we can find the inverse Laplace transform. But that polynomial is still pretty complicated. So then this special notation is introduced. Yeah. Little l of sub n. Yeah, so that's that, Laguerre's, special polynomial is defined. Yeah. So the definition, yeah. Here you can see the definition this is the definition. Yeah. This definition, the same as you calculate. So you do the binomial expansion on the numerator, then you do the, term by term inverse Laplace transform. So you will get that. Yeah, so this derivative. Yeah, so so if you calculate derivative, yeah, so you can compare with that. Yeah. So that special polynomial. Yeah. All right. Yeah. So that's another example. Yeah. All right. Then B.4, Dirac's delta function. Yeah, so this is another important topic. Yeah. Dirac's delta function. We want to look at the Laplace transform. Yeah. First, the definition of Dirac delta function. Yeah. Then we look at some examples. Definition of Dirac's delta function. Yeah, I mentioned before, this function is very special. So when we understand it, yeah, so we need to really, use our abstraction thinking to understand. Very abstract. Yeah. So first, let me explain this function. All right. So here, when we define this Dirac's delta function, we do not define it directly, indirectly, yeah, because if we define it directly, it's very hard to understand. So we define it indirectly. So we introduce a new notation, f sub k function shift, yeah, t minus a, yeah, so that shift to a. Yeah. Remember our Heaviside function, we do this kind of shift. Yeah. Shift a units to the right. Yeah. Here, yeah. So this function, yeah, non-zero in this interval, yeah, from a to a plus k. Yeah. So there is a box. Yeah. So the graph. So if we draw the graph, it's like this. There is a box, bar. It's a bar. Okay, all right. Yeah. So the width of this bar is k, right? Yeah, k. The height of this bar is 1 over k. 1 over k, the height, the width. So the area of this bar, yeah, k times 1 over k. Area is 1. Area is 1. All right. Yeah. So that's special function. Yeah. But this special function, now we want to change this k. We want to change that k. Yeah. So k is a parameter. Yeah. So we can adjust. Yeah. But this k, yeah, we want to make it approach to 0. Not to infinity. Approach, make it this k very small. Very small. All right? Yeah? So here. Yeah. All right. Make k goes to 0. Yeah. Yeah. When k goes to 0, look at this function. The shape of this function. Yeah. Skinny. It becomes very skinny. Yeah? Yeah. But the area always 1. Area, no change. Yeah. But, yeah. So in this way, the definition. So the function can be defined. So this fk function can be defined. Yeah. Although the shape is very weird, yeah, but function can be defined. No problem. The definition of function. But the question is, when k approaches to 0, what is the limit of this function? That's questionable. The limit of this function. The question, does it exist, right? Yeah, because when you talk about limit, the first thing you need to answer is, does the limit of the function exist or not? That's a big question. Yeah. All right. Yeah. So actually, the limit does not exist. The limit, it does not converge. The limit does not exist. All right? Yeah? So that's the problem. That's the problem. The limit does not exist. Yeah. So then why we do this, right? The limit does not exist. Why we do this? Yeah. Yeah. The reason, yeah, there is some good reason to do this. Yeah. Because we can use this very special function, we can solve many interesting problems. Yeah. It's useful. Yeah. All right. But the limit does not exist. Yeah. So that means we cannot write it out, right? We cannot write the specific limit function out. Clear, the formula of the limit. Nobody can write it out. Yeah. Then, how to handle it? Yeah. So then, Dirac, yeah, introduced the special notation delta function. Yeah. Yeah. We use this notation to represent it. Notation, yeah. Delta function, to define the delta function equals the limit. Yeah. Yeah. But we know the limit does not exist. We cannot write it out. So that kind of thing, so abstract, something very weird, yeah. But this object, so now let's treat it as an object. This object is useful. And in real world applications, there are many phenomena can be modeled by this function. Yeah, because many phenomena can be modeled by this strange function. Okay? Yeah? So it's useful. Yeah, later we will see it. Yeah. Later we will see. Yeah. How to model, some special phenomena. Yeah. All right. So here we use this notation. All right. Dirac delta function. Yeah. All right. So here we use the word function here, yeah, but actually it's based on the definition of the function. Yeah? So in our calculus or pre-calculus, we need to define function. If we apply the definition of function, it's not a function. It's not a valid function. Okay? Yeah? Yeah, but people still call it Dirac function, a delta function. Delta function. Yeah. Yeah. So then, I remember I mentioned once before, but at that time, because it was too early, so you may not have impression. So here, now we are at this point. Yeah. So this delta function is not a real function. Yeah. So then, some people call it, use a slightly different name to call it. Yeah. So it's not a valid function. Yeah. So some people call generalized function. Generalized. Yeah. Yeah. So we generalize it a little bit. Okay. Yeah. So one way to call it generalized function. generalized function. Yeah. Not a normal function. Yeah. So it's a generalized function. Yeah. Another popular name in PDE. Yeah. So when people solve PDE, so use this kind of functions called a distribution. Yeah. So in PDE context, yeah. So this kind of functions also very useful. Yeah, but they call it distribution. Yeah. Dirac function just one of the distributions. There are many different kinds of distributions. Yeah. So those distribution, yeah, if we treat them as functions, they are not functions. So they are not valid functions. Yeah. But they have some special properties. Yeah. So that's the about the background of this function. Yeah. All right. Or unit impulse function. Yeah. So from the shape, you can see it's an impulse. Impulse. You know, the change like impulse phenomenon. Unit. Why unit? Because the area is 1, so we call it unit. It's a unit impulse function. Yeah? All right. Yeah, so let's take a break. So when you come back after the break, so let's study the properties of this function. Why it is so useful.